Welcome to MasterCode. Episode 4, and we're going deep into Python for security work. If you ask professional penetration testers what single skill multiplied their capability the most, the answer is almost always Python. Not a specific tool. Not a certification. Python. Because Python is what lets you stop being a consumer of other people's tools and start being a creator of your own. And that transition changes everything. When you understand how a port scanner works at the code level, you use Nmap differently. When you've written your own SQL injection detector, you understand what SQL map is actually doing. When you've built a reverse shell from scratch, you understand what defenses catch it and which ones miss it. The depth of understanding you get from writing these tools is not achievable any other way. We're covering environment setup, network programming with sockets, web testing with the requests library, packet crafting with Scapy, SSH automation with Paramiko, binary exploitation with pwntools, and automation workflows that chain everything together. Every code block you see today is runnable in your Kali VM right now. The setup takes about 5 minutes. Bring your terminal. Let's start coding. The ethical context for this episode is important, so let me be direct. Python code is a tool and your intent and authorization determine whether using it is legal. Writing a port scanner in Python and testing it against your own VM is completely legal and an excellent learning exercise. Running that same port scanner against a company's network without explicit written permission is unauthorized access and a criminal offense. The code is identical. The authorization is what differentiates legal security research from hacking crime. Every tool we build in this episode gets tested exclusively in your lab environment. Your Kali VM running against your Metasploitable VM on a host-only network. That's the safe environment. When you move into authorized testing on real targets through CTF platforms, bug bounty programs, or professional engagements, you bring these skills with you. The Python skills transfer completely. The authorization requirement never changes. I want to say something about distributing offensive code as well. Publishing a Python exploit to GitHub, posting it publicly, sharing it in forums, these actions come with responsibility. Understand who might use your code and for what purpose before making it public. The security community has norms around responsible disclosure and tool distribution. Learn them and respect them. Your reputation in this field is built over years and can be damaged quickly by careless handling of offensive capabilities. With that clear, let's get to work on building some excellent tools. Python is the dominant language in security research, offensive security tooling, and CTF competitions, and there are concrete reasons for this that go beyond preference. The syntax argument is real. Python code reads almost like English pseudocode. When you're in the middle of a CTF competition or a time-sensitive engagement, you want to prototype ideas quickly without fighting the language. Python lets your brain focus on the security logic rather than the syntax. The library ecosystem is genuinely extraordinary. The requests library handles HTTP so well that building a web testing tool is sometimes just 2 or 3 lines of code. Scapy lets you craft any network packet you can imagine. Paramiko provides SSH capabilities. Impacket handles Windows network protocols. pwntools provides a complete binary exploitation framework. These libraries exist because the security community built them for security work. Rapid prototyping matters in the field. When you're exploring a target and you want to test a hypothesis about a vulnerability, you want to write and run that test in minutes, not hours. Python is the language where ideas become running code fastest. Cross-platform capability means your tools work everywhere. Write a Python script on Kali, move it to a Windows target, and it runs. This is important when you're doing post-exploitation on diverse environments. And reading existing security tools source code is a massive learning accelerator. Metasploit modules are written in Ruby, but many supporting tools are Python. Being able to read and understand Impacket's implementation of pass the hash teaches you the protocol behavior at a level that no tutorial can match. Python is not just a tool. It's the language of the security. Let's get your Python security environment set up properly before we write any real tools. The most important decision is whether to use a virtual environment for your security tools. I strongly recommend it. A Python virtual environment is an isolated environment where you can install packages without affecting your system Python installation. This prevents dependency conflicts when different tools need different versions of the same library. Create your environment with Python 3-m followed by a path, activate it with source and the activate script, and then install packages inside it. Everything stays clean and organized. Your core security libraries are requests for HTTP communication, Paramiko for SSH automation, Scapy for packet crafting, and pwntools for binary exploitation. Install Impacket for Windows protocol support when you start doing Active Directory work. The basics of Python for security work revolve around a handful of core concepts. Bytes objects rather than strings handle raw network data. The socket module is your direct interface to network communication. The subprocess module runs external tools and captures their output. The OS module handles file system operations. Everything else is built on these foundations. One important nuance: many security operations require root privileges because they operate at the raw socket or network device level. Running your Python scripts with sudo grants those privileges. Scapy, ARP operations, and raw socket programming all require this. Structure your scripts to check for root if they need it and fail gracefully with a helpful message if they don't have it. Building a port scanner from scratch is the classic first exercise in Python security programming, and for good reason. It introduces you to network sockets, concurrency, and the fundamental mechanics of how network scanning actually works. Let me walk you through the thought process. A port scanner's job is simple in concept: try to connect to a port, record whether it succeeds or fails. The socket module provides exactly this capability. You create a socket object, set a timeout so you don't wait forever for unresponsive ports, attempt to connect, and report the result. The single biggest performance issue with a naive scanner is that it's sequential. Without threading, you connect to port 1, wait for it to succeed or timeout, then try port 2. On a 1-second timeout, this means scanning 1,000 ports takes 17 minutes. That's completely impractical. Thread pool executor from the concurrent.futures module solves this by running many connection attempts simultaneously. With 100 workers, your 1,000 port scan takes seconds instead of minutes. The key lesson here is understanding the difference between sequential and concurrent execution. This concept applies everywhere in security automation. When you're running subdomain brute force or credential testing, threading is the difference between impractical and practical. Understanding this at the code level, rather than just seeing GoBuster run fast, gives you the intuition to make intelligent decisions about concurrency in every tool you build. Always add timeout handling, always add exception handling for refused and filtered connections, and always consider what your output should look like before you start coding. Clean output from a tool matters more than you might think. Here's the complete implementation of your threaded port scanner. Let me walk through every line so you understand exactly what's happening. The import section brings in socket for network connections and thread pool executor for concurrency. We define a scan function that takes a host and port. Inside, we create a socket object, set a half-second timeout, and attempt to connect. If the connection succeeds, port is open and we print it. If any exception occurs, connection refused, timeout, or network unreachable, we do nothing. This simple try-except structure handles all the normal error cases without crashing your program. We define our target host and then use thread pool executor as a context manager with 100 worker threads. The map call applies our scan function to every port from 1 through 1024 simultaneously, running up to 100 at a time. This is the complete scanner. 100 lines of tool documentation collapsed into 15 lines of Python that actually runs and actually works. Now, how does this compare to Nmap? Nmap does exponentially more than this. Service version detection, OS fingerprinting, script scanning, UDP scanning, stealth SYN scanning, output formatting, timing control. Your scanner just checks if a TCP connection succeeds. Use Nmap for real work. But understanding that Nmap is fundamentally doing some version of what you just wrote, with enormous additional sophistication around it, gives you a mental model that makes Nmap's flags and output more meaningful. You know what's happening under the hood. Banner grabbing is the natural extension of port scanning. Once you know which ports are open, you want to know what's running on them. Many services send identifying information as soon as you connect, before you send anything at all. This information is called a banner. The implementation is straightforward. After successfully connecting to a port, instead of immediately closing the connection, we wait for data using the receive function. We set a 2-second timeout to avoid hanging on services that wait for input before responding. The received bytes get decoded to a string and cleaned up. What you get back is often extraordinarily useful. An FTP server announces its software name and version. SSH servers declare their protocol version and software name. Database servers sometimes announce the database type and version. Web servers without proper security configuration announce the web server software and its version in response headers. Version information is valuable because it maps directly to known vulnerabilities. When your banner grab reveals that a server is running ProFTPD version 1.3.5, your immediate next step is searchsploit prof 1.3.5. If there are known exploits, you now have your path. If the SSH banner reveals OpenSSH 7.2 p2 on Ubuntu, you can look for vulnerabilities specific to that combination. This is exactly what automated vulnerability scanners do at scale. They collect banners, map versions to CV databases, and report potential vulnerabilities. Your simple Python banner grabber is doing the same thing manually, and understanding that process is valuable even when you're using automated tools later. The requests library is the most downloaded Python package in the world, and for good reason. It makes HTTP incredibly easy to work with. For web application testing, this translates directly into rapid development of custom testing tools. Let me walk through the capabilities that matter most for security work. Basic GET and POST requests are just requests.get and requests.post with the URL. But the real power comes from the keyword arguments. The headers parameter lets you set any HTTP headers you want, including user agent spoofing, custom authentication headers, or headers needed to bypass security controls. The cookies parameter lets you manage session cookies manually, essential for testing authenticated functionality. The proxies parameter is one you'll use constantly. Set it to route your requests through Burp Suite running on localhost port 8080. Your Python tools requests become visible in Burp's proxy history, where you can see exactly what's being sent and received in full detail. Sessions are critical for testing anything that requires authentication. A request session object automatically maintains cookies across multiple requests. You log in once, the session stores the cookie, and all subsequent requests in that session include the authentication cookie automatically. This makes testing post-login functionality trivial. Response analysis gives you everything the server returned. The status code number, the full headers dictionary, the response body as text or bytes, and for JSON APIs the parsed JSON as Python data structures. Your web testing logic makes decisions based on all of these. Learning requests deeply makes every web security tool you write significantly better. Subdomain enumeration is one of the first steps in web application reconnaissance, and Python makes it trivially automatable. The concept is simple: take a word list of common subdomain names, check if each one resolves to an active web server for your target domain, and report the ones that do. The implementation uses requests to make HTTP connections to each possible subdomain. Setting allow _redirects to false is important because some servers redirect invalid subdomains to a catch-all page with a 200 status code. By not following redirects, you see the actual response code and can distinguish real subdomains from redirect traps. The content check can be extended. Instead of just checking status codes, check response content length or look for specific strings in the response body to reduce false positives. Threading is essential here because you're making hundreds or thousands of HTTP requests. Without concurrency this would take hours. With 100 threads it takes minutes or even seconds depending on network speed. The word list choice matters enormously. The SEC lists repository on GitHub, which you should clone to your Kali VM immediately, contains subdomain word lists with millions of common names from research on real internet hosts. The right word list turns 3 subdomain discoveries into 30. Real subdomain brute forcing at scale uses tools like FUF and amass, which handle rate limiting, DNS resolution, and multiple discovery techniques simultaneously. But understanding the HTTP request-based approach at the code level makes you a better user of those tools because you understand the trade-offs they're navigating. Directory brute forcing is web reconnaissance's equivalent of port scanning. You're trying to discover URLs that exist on a web server that aren't linked from the main site. Administration panels, development endpoints, backup files, configuration files, all of these are findable by systematically requesting paths from a word list. The Python implementation follows the same pattern as the subdomain scanner but adapted for URL paths. Load your word list, make requests to each path, check the response code. The interesting response codes are not just 200 for success. You want to know about 301 and 302 redirects because they often point to real content. You want to know about 403 forbidden responses because they indicate a path exists but access is restricted. That restriction might be bypassable through other means. The 404 not found is the only response you discard. Content length checking prevents false positives from servers that return 200 for every request with a custom not found page. If the length is consistent across all your requests, that's a catch-all page, not real content. Filter those out by recording the length of the first few responses and ignoring responses with the same length. Your word list selection is critical. SEC lists contain specialized word lists for different scenarios: general web directories, API endpoint names, backup file names, technology-specific paths. Use the right word list for your target's technology stack. A PHP application has different interesting paths than a Django app. And always run multiple word lists. One pass misses what another catches. Tools like GoBuster and FerrixBuster have features and performance that your Python script won't match. SQL injection is still one of the most common and impactful web vulnerabilities despite being a problem that has been understood for over 20 years. Python can automate the detection phase to quickly identify potentially injectable parameters before diving into manual testing or SQL map. The detection approach is to send known injection payloads and look for error messages in the response that indicate the payload disrupted the SQL query. A single quote character breaks SQL syntax in most contexts and causes database error messages to appear in the response. SQL comments, union select attempts, and ordering tricks reveal different types of injection vulnerability. The error strings we check for are database-specific error messages that appear when the SQL query fails. MySQL shows MySQL_fetch errors. Oracle shows ORA-prefixed codes. MSSQL and ODBC show their own patterns. Checking for these in responses after sending injection payloads is a reliable first-pass detection method. The baseline comparison approach is more sophisticated. Make a normal request and save the response. Then send the same request with injection payloads and compare the responses. Significant differences in length or content indicate the payload affected the application's behavior, which suggests injection. Your Python detector is intentionally simple. It finds obvious error-based injection. SQLmap does exponentially more: time-based blind injection, Boolean-based blind injection, out-of-band extraction, automatic payload adaptation based on database type. Once your Python script flags a parameter as potentially injectable, SQLmap is your next tool. But understanding what SQLmap's first stage looks like at the code level makes you a better interpreter of its output. Password attacks are a core component of penetration testing, and Python makes both login brute forcing and hash cracking straightforward to implement. Let me walk through both. The HTTP login brute forcer takes a URL, a fixed username, and a word list. It reads the word list line by line, constructs post data with each password, submits it, and checks the response. The key challenge is knowing what success looks like. Each application is different. Some redirect to a dashboard on success. Some return a different page content. Some use a JSON API that returns a success field. Your script needs to know the success indicator for the specific target. In the example, we check for the absence of the word invalid in the response, but this needs to be adapted per target. Threading is essential for password attacks too. Sequential requests against a rate-limited login form could take days. With threading and sensible rate limiting to avoid account lockout, the same test takes hours or minutes. Hash cracking in Python uses the hashlib module, which implements all standard cryptographic hash functions. The approach is the dictionary attack. For each word in your word list, compute its hash and compare to the target hash. The speed of Python hash cracking is dramatically lower than Hashcat, which uses GPU acceleration. For training and understanding the algorithm, Python is fine. For actual hash cracking and engagements, use Hashcat exclusively. It cracks hashes millions of times faster than any CPU-based Python implementation. Understanding the algorithm in Python makes you appreciate why GPU acceleration changes the game so dramatically. Scapy is one of the most powerful tools in the security Python ecosystem. It lets you craft, send, receive, and analyze any network packet at any protocol layer, all in Python code. This is not a wrapper around other tools. This is direct packet construction and transmission at the network layer. The fundamental Scapy approach is layer stacking using the / operator. An IP layer stacked on a TCP layer on a payload gives you a complete TCP packet. Scapy handles all the checksums, packet lengths, and protocol details automatically. You define what you want, Scapy handles the mechanics. The send functions are your transmission options. SR1 sends one packet and waits for one reply, returning that reply as a Scapy packet object you can inspect. SRP does the same at layer 2, including Ethernet frames. Send at layer 2 and send at layer 3 transmit without waiting for a reply. ARP scanning demonstrates Scapy's power elegantly. You build an ARP request asking who has each IP address, broadcast it over Ethernet, and collect replies. Each reply contains the IP and MAC address of a live host. This discovers hosts that don't respond to ICMP ping but do respond to ARP, which is common on hardened hosts. SYN scanning constructs TCP packets with only the SYN flag set, which is what TCP connection initiation looks like. A SYN-ACK response means the port is open. An RST response means it's closed. No response means filtered by a firewall. This is the same technique Nmap uses for its stealth scan mode. Scapy lets you implement it yourself and understand exactly what you're looking at. Let me walk through the Scapy code examples in detail so you understand what every line does. The ARP-scan function creates an ARP request targeting a network range in CIDR notation like 192.168.1.0/24. Scapy expands this to individual ARP packets for each IP in the range automatically. The Ether layer sets the destination MAC address to the broadcast address, which means every device on the local network receives the packet. The SRP function sends the packet at layer 2 and waits for responses. It returns a tuple where the first element contains the sent and received packet pairs. We iterate through these pairs and print the IP and MAC address from each reply. This gives you a complete map of live hosts on the network including their hardware addresses. The SYN port scan function constructs an IP layer with the destination host and a TCP layer with the SYN flag set. The SR1 function sends this and waits for one response. The response analysis checks if a TCP layer is present in the reply and if so examines the flags field. A value of 0x12 in hexadecimal corresponds to the SYN and ACK bits both being set, which is the SYN ACK response that indicates an open port. After detecting an open port, we send an RST packet to cleanly close the half-open connection. Without this RST, the target system accumulates half-open connections which is both detectable and rude to the target system. This cleanup step is part of doing SYN scanning responsibly on authorized targets. The raw code gives you direct insight into what Nmap's-SS flag actually does at the packet level. The Python reverse shell is a fundamental concept in penetration testing and CTF competitions. Understanding how it works at the code level is essential for both using it effectively and understanding how to defend against it. Let me walk through the implementation. The shell establishes a TCP connection to your attack machine using the socket module. Once connected, it redirects the three standard file descriptors, stin, stout, and stare, to use the socket's file descriptor instead. This means any input your shell process reads comes from the network socket, and any output it writes goes to the socket. Then it executes bash in interactive mode. The net effect is that commands you type on your listening netcat session are sent over the network, received as stin by the bash process, executed, and the output is sent back over the network and displayed in your netcat session. You have a remote interactive shell. The one-line version compresses this into a single Python 3-C command that can be executed as a single string in various contexts. You'll see this in web shells, command injection exploits, and argument injection vulnerabilities. The key operational detail is that you start your netcat listener first, then trigger execution of the payload on the target. Your listener catches the incoming connection. From that moment you have interactive access. Remember that this technique leaves clear indicators in system logs and network traffic. On authorized tests this is documented and expected. On unauthorized systems it's evidence of unauthorized access and a criminal act. The technique is legitimate in your lab and in authorized engagements. Nothing else. Paramiko turns Python into a powerful SSH automation tool. The use cases in security work are substantial. Credential testing across many hosts, automated command execution as part of an exploitation workflow, and file transfer automation during post-exploitation. The setup pattern is consistent across uses. Create an SSH client object, set the missing host key policy to auto-add so it doesn't prompt about unknown hosts, then call connect with the target host, username, and credentials. On success you have an authenticated SSH session object. Executing remote commands is done with the exec_command method. It returns three stream objects, stin for sending input, stout for reading command output, and stare for reading error output. Read from stout to get command results. The output comes back as bytes, decode it to get a string, and process it however you need. For file transfers, call open_SFTP on the connected client to get an SFTP session. SFTP.put uploads a local file to the remote path. sftp.get downloads a remote file to a local path. This is functionally equivalent to SCP but controlled entirely from Python code. The credential testing use case is valuable for authorized password auditing. Loop through a list of username and password combinations, attempt to connect for each, catch the authentication exception for failures and log the successful connections. This is more flexible than Hydra for custom authentication logic. Paramiko's real power comes when you combine it with the other tools: scan with your port scanner, grab banners to identify SSH services, test credentials with Paramiko, then automate post-exploitation commands on successful hosts. Let me give you an honest comparison between building your own Python tools and using dedicated professional tools, because there's a right way to think about this that most beginners get wrong. When you're learning, building tools is the single most effective way to develop deep understanding. Writing a port scanner teaches you TCP sockets, timeouts, concurrency, and exactly how Nmap's basic scan works under the hood. Writing a web brute forcer teaches you HTTP request structure, response codes, session handling, and what GoBuster is actually doing. This understanding makes you a dramatically better user of the professional tools. You know what their options mean because you've implemented the same concepts yourself. In professional work and in CTF competitions where time matters, you use dedicated tools. Nmap is not just a port scanner. It's 20 years of optimization for accuracy, stealth, and detection of edge cases that your 15-line scanner will never handle correctly. SQLmap handles dozens of injection types, database-specific techniques, and evasion strategies that would take months to implement yourself. Hashcat uses GPU acceleration for hash cracking performance that CPU-based Python can't approach. The best approach combines both worlds. Build tools to learn the concepts. Use professional tools for actual work. Write Python to glue professional tools together, automate workflows, and handle cases where no existing tool fits your exact need. Read the source code of professional tools written in Python to continue learning from the best implementations. Your Python knowledge is what makes your entire security toolkit more powerful, even when you're not writing the primary attack tools yourself. pwntools is the standard framework for binary exploitation in CTF competitions and security research. It abstracts away the repetitive parts of binary exploitation so you can focus on the vulnerability analysis and exploit logic. If you're planning to compete in CTFs, pwntools is not optional. Install it immediately. The core workflow in pwntools starts with connecting to your target. The remote function connects to a network service. The process function interacts with a local binary. Both provide the same interface for sending and receiving data. The recon method reads data from the target until it sees a specific byte sequence, then stops and returns everything received up to that point. This is essential for interactive exploits where you need to wait for prompts before sending your payload. Sendline sends a line of data followed by a new line, which is what most interactive programs expect. The interactive method drops you into a live interactive session with the target process. Use this after your exploit executes to interact with whatever shell or program your exploit spawns. Buffer overflow exploitation uses pwntools cyclic pattern generation. The cyclic function generates a De Bruijn sequence, a pattern where every substring of a given length is unique. Send this pattern as input to a vulnerable program, find the exact bytes that overwrite the return address from the crash, and cyclic_find converts those bytes back to the offset. The p64 function converts integers to 8-byte little-endian packed format, which is what you need to provide 64-bit memory addresses in payloads. pwntools handles all of this cleanly so your exploit code focuses on logic, not byte manipulation. The real power of Python in security work is automation, connecting tools together, parsing outputs, making decisions based on results, and running the next tool automatically. This is where Python elevates your workflow beyond what any single dedicated tool can do. Nmap's XML output is designed for programmatic consumption. Run map with the -aux flag to save XML results. Python's xml.atree.elementtree module parses this into a navigable data structure. Extract hosts with open ports, their services, versions, and script results. Use this structured data to drive the next phase of your assessment automatically. Feeding service versions to searchsploit via subprocess means you automatically get vulnerability suggestions for every discovered service without manually running searchsploit for each one. This turns a 20-minute manual process into a 30-second automated one. Metasploit's RPC API is available via the MSFRPC Python library. Connect to a running Metasploit instance, create console sessions, execute modules with specific options, and retrieve results. This enables fully automated exploitation workflows. Nmap discovers a vulnerable service, your script identifies the right Metasploit module, automatically configures it with the target details, runs it, and reports the result. Report generation is where Python saves enormous time in professional work. Collect all tool outputs into Python data structures throughout your assessment. At the end, run a report generation script that formats everything into a professional HTML or PDF report. The difference between manual copy-paste reporting and automated report generation is hours of tedious work per engagement. Build this once and use it forever. Let me give you a clear summary of the 6 Python libraries that handle 90% of security work. Install all of them in your virtual environment today. Requests is your HTTP foundation. Every web application test, every REST API interaction, every web scraping task runs through requests. It handles TLS, cookies, sessions, redirects, authentication, and proxy routing. If you're doing any web security work, requests is your starting point. Scapy is your network packet toolkit. ARP scanning, SYN scanning, custom protocol implementation, packet sniffing and capture, traffic analysis. Scapy requires root but gives you direct access to the network stack at a level that no higher-level library provides. Paramiko handles SSH. Remote command execution, file transfers, credential testing, tunnel creation. Anytime you need to interact with systems over SSH programmatically, Paramiko is the right tool. pwntools is your CTF binary exploitation framework. Buffer overflows, format string vulnerabilities, return-oriented programming, remote process interaction. If you're doing CTF competitions that involve binary exploitation challenges, install pwntools immediately. Impacket implements Windows network protocols in Python. SMB authentication, Kerberos tickets, NTLM authentication, pass the hash attacks, DCOM. Essential when you're working in Windows and Active Directory environments. The learning curve is steeper but the capability is unmatched. And the cryptography library implements cryptographic primitives and protocols. Hash functions, symmetric and asymmetric encryption. CTF competitions are where your Python skills get tested under time pressure and where automation makes the decisive difference between solving challenges and running out of time. Let me describe the workflow that skilled CTF players use. The recon phase is always scripted. You shouldn't spend 5 minutes manually running the same map, gobuster, and service enumeration commands on every machine. Write a Python script that does your standard initial recon automatically. Start at the moment a new target is available. Go work on something else. Come back to structured results. Decoding challenges appear in almost every CTF. Flags are often wrapped in layers of base 64, hex, ROT13, binary, or custom encodings. Instead of trying each one manually, write a Swiss Army decoder that tries all common encodings automatically and outputs anything that looks like printable text or matches the flag format. 5 minutes of writing this script saves minutes on every decode challenge for the rest of the competition. Exploit automation is critical. When you manually work out how an exploit functions, immediately script it before moving on. If you need to re-exploit the target for any reason, a working script runs in seconds. Manual re-exploitation from memory takes minutes and introduces errors. Flag extraction with regex prevents the embarrassing situation of missing a flag buried in large output. Write a simple function that searches any output string for the flag format pattern using regular expressions. Call it on every tool's output automatically. Time-based challenges require Python's threading module for millisecond precision. Race conditions, timing attacks, and synchronized multi-step exploits all benefit from programmatic control of timing. Episode 4 is done and you now have a real Python security toolkit. Port scanners, banner grabbers, web reconnaissance tools, SQL injection detectors, login brute forcers, hash crackers, packet crafting with Scapy, SSH automation with Paramiko, and reverse shell understanding. Most importantly, you understand how these tools work at the code level. That understanding changes how you use every professional tool in your arsenal going forward. Here's your action item from this episode: build one complete tool this week. Pick any concept we covered and implement it fully. Add error handling. Add threading. Add clean output. Add results saving to file. The act of finishing one complete tool, even a simple one, is worth more than watching 10 more tutorial videos. The friction of debugging real code creates real learning. Episode 5 covers web application security, which is where the majority of professional penetration testing work happens. We're covering OWASP Top 10 in depth, Burp Suite Mastery, SQLi, XSS, authentication vulnerabilities, API security testing, and the complete methodology used by professional web application penetration testers. Web app security is also where bug bounty hunters find real money. We're going deep. Subscribe so you catch episode 5 when it drops. And if this episode taught you something useful, a like helps this channel grow. See you in episode 5.